Welcome everyone again to Consumer Reports' webinar all about microplastics, what they are, why we should care about them, and why they're so hard to test, and what we're doing about that. My name again, I'm Alan Smith. I'm an organizer here with Consumer Reports. I use he, him pronouns. I'm calling in to this webinar today from Brooklyn, New York. And like I said, we're going to be talking about microplastics today. We're going to be talking about how to test specifically for microplastics in food and water to try to get to the bottom of how they are getting in from our environment into our bodies. Um, we're going to be talking about why it's so expensive and difficult and time consuming to test for microplastics and why Consumer Reports and to try to understand more about microplastics, ran a crowdsourced challenge with our partner Lifeguard to work towards a quicker and more inexpensive test for microplastics that consumers could use without special training. So we invited experts and practitioners from around the globe to help us find a solution that would advance our ability to detect microplastics in our own lives. Um, and today I'm excited to get to introduce you to two of our winning teams from that whole experience. Oh, hey, Scott, let me get you 1 second here. I'm going to grab you. Um, I'm going to introduce you to those winning teams and also some of our Consumer Reports folks who are here as well. We're going to talk about microplastics and what they are. We're going to talk about the challenge that we ran. We're going to talk about two of those winning ideas. And I'm going to be joined in all of this by Samantha Bennett, the co-founder of Lifeguard, the organization I mentioned, and she's going to tell you a little bit more about who they are and what they do. I'm joined by James Rogers, who's the director of product and food safety here at Consumer Reports, and is knows more about the subject than I guess I will say has forgotten more about microplastics than I will ever know. In just a second, I will have Scott Coffin pulled from the masses of participants and promoted to the role of being able to speak as a panelist. Give me 1 second, Scott. I'll get you in here. And then I'm also really excited to introduce you to the two winning teams who we're going to be hearing from today. Team one, made up of Nur Alif Fathraman, Esra Kotab Abbas, and Listia Aka Anjugrani, who will tell you about their amazing idea about how to test for microplastics, and then representing a team with him and his brother, Syed Umar Ahmed, who will also be talking about his awesome idea. And those folks will be the run of show, really. Before I get there, unfortunately, I have to do what I always have to do in this instance, which is a little bit of housekeeping. Um, if you've been to one of these before, you've heard this, but we are, one, recording this to share, and we will send around a video tomorrow for everyone. So if something zips by or you think you want to go back and hear a particular explanation again, totally cool. You'll be getting a video in the not too distant future. Um, the links that we will be dropping into the chat today about microplastics, about this challenge, about all sorts of different things will also be grabbed and put into this omnibus email that I will send around. So if something, again, zips by that you think you want to read, don't worry too much. You'll have a chance to see it again. Finally, closed captioning is available. You should see a little either a CC option on your screen or maybe 3 dots to the far right, which says more. If you click on that more button and you want to find closed captioning there, that should be available. We will be talking quickly and we will be talking about some fairly technical stuff today. So if it's getting hard to follow, closed captioning is actually a decent way to keep up with that flow. I will try to remind myself to speak slowly and clearly, and our panelists and participants will do our best. But there might be some acronyms and some things speeding by that you want to get another look at. And then finally, a lot of you have already said hi in chat. I love that. Chat's a great way to ask questions and to interact with us today. There's also a Q&A function, which you can use to mark questions that you have for our panelists to circle back to. So we'll be keeping an eye on both of those. And then we do have some ground rules today. It's not going to be a problem. Y'all are going to be awesome, but we like to say these up top. Please assume best intentions of everyone participating in this webinar. Please be mindful of your fellow participants who are coming from different life experiences. Please speak to your own perspectives and stories and refrain from any personal attacks or comments on appearance, language, etc. And by attending this webinar, you are agreeing to these ground rules. So it's not going to be a problem. But if we have to remove anybody, that's why. And those are the ground rules. The rules of the road today. Okay, that is a lot of monologuing from me, but I think that that's everything we need to get out of the way for our conversation today. And so I am going to toss now, or bring in now, Jim Rogers, who Dr. James Rogers, who is our director of food safety. Jim, how are you today? Where are you calling in from?
I am doing fine. I'm calling in from the Washington, D.C. area because my main base is our office in D.C.
And Jim, what should folks on this call know about microplastics? What are they?
So, we're going to talk about a couple of things. First, we'll define microplastics. Microplastics are considered small plastic particles, and they range from microplastics, which are, could you go back one?
Yep.
Yeah, okay. Small particles about the size of a sesame seed, all the way down to microscopic pieces of plastic, microscopic, they're usually referred to as nanoplastics. There are two main sources, standard sources. One would be either the nurdles, which are the raw plastic pellets that are then further processed to make the plastic product, or microbeads. There were some cosmetics, mostly banned now, but there were some cosmetics that would have these very small plastic beads in them to help with smoothness, ease of application of uh, uh, the makeup or whatever, but they've been pretty much banned now. Then secondary, which we consider breakdown products. So these would be from larger plastic items that then these pieces would shear off into smaller plastic pieces of plastic, and they don't biodegrade. So that's an important thing to remember. Where they come from would be the synthetic fibers in our clothing, such as nylon or polyester. You wash these clothes, they shear off in the washing machine, they go through the wastewater, and they end up in our rivers and streams, etc. Tire dust. Most tires are made of synthetic products, and so they can shear off and end up in our water. And then packaging, such as water bottles, food containers, plastic bags that eventually degrade and crumble in sun, and then these particles again get into our water. Next slide, please. So this is a picture that shows you that you can go from the larger microplastic size of plastics down to the smaller plastics. And so on the left-hand side are the larger pieces, and then eventually, because of shearing and breaking down, they end up in the nano size. And then as you see on the right-hand side, this is a cross section of a microscopic slide of human skin. And as you can see, the microplastic can actually get into the cellular areas of your body and potentially cause problems. And we'll talk about that in a second. Next slide, please. So how bad are they? So one thing is in the environmental side, I already mentioned that they don't biodegrade, but they can also be ingested with the smallest organisms in the food chain and move all the way up to us. So you can imagine the zooplankton, which are very small animals in the water. They can take up microplastics, and they're eaten by fish, and then little fish are eaten by bigger fish, and bigger fish are eaten by bigger fish, and then we eat fish. And so we can have an environmental source of microplastics in our diet. The other issue is that these pieces of plastic can be like chemical sponges. So not only the chemicals that are used to make them called plasticizers, but they can also absorb heavy metals and pesticides in the water. And then we ingest them and they release these chemicals into our body. And the other point to know is that they're everywhere. They've been located from the peak of Mount Everest down to the lowest depths of the ocean, the Mariana Trench. So they're everywhere. What are the concerns for humans? Well, we breathe, we eat them. The science, the public health science about what they cause clinically is still being worked on. But there are two areas that there is a concern of. Number one is the physical or the chronic inflammation that can happen when you have these microplastics in lung tissue, in the blood, in reproductive organs such as placentas, in the testes. And then there's the chemical exposure. Not only these hitchhiker chemicals can come along, but they're plastic. And we at Consumer Reports have reported on chemical additives, the plasticizers such as bisphenol A and phthalates. And so, with these plastics being in the body, they can release these harmful chemicals and affect bodily functions. Okay, next slide, please. So we at Consumer Reports are really interested in microplastics, especially in food and water, and we've written a story or two about microplastics, but without testing. Well, why is that? Well, number one, when you work with microplastics and you're trying to isolate them and identify them, you're dealing with a needle in the haystack. You're dealing with trying to get small pieces of plastic out of a very complex sample matrix, such as food. So if you really want to try to identify, number one, isolate and identify these, you have to be able to remove everything else in the food, such as the fats, the proteins, the sugars, all of the organic material. And you have to figure out a way to digest that with either acids or enzymes. So then you can get to the plastic particles and then analyze them. And that's not easy. You have to have a method for each food that you're trying to analyze. Second is identification. I put up FTIR and Raman spectroscopy as two of the ways that are used in laboratories to actually analyze microplastic, but they are very complicated machines. They're very expensive. You have to have trained personnel. Most commercial laboratories that analyze food do not have this equipment, so you tend to have to talk to academic labs to work. And we have talked to some about doing some analysis. The costs average that we were quoted was between $3,000 and $4,000 per sample. We're a nonprofit and we live on donations. And so that is way too expensive for us to be able to analyze food and water for microplastics. And this is when you want to identify the plastic and you want to go down to the nanoplastic level, the smallest particles. It is estimated that if you look at a sample, 90% of the plastic in the sample is a nanoplastic, the smallest size that you can dip. And then the final thing is that you have to ask yourself, are you detecting everything? So we're kind of decent at looking at microplastics. It's not as good as looking at nanoplastics. The other thing is that you also want to know what type of plastic it is, so you could hopefully trace it back to the source, but you want to get those small particles too. And so those are some of the challenges that we're facing in the laboratory about detecting microplastics, nanoplastics in samples. And so that's why I was very enthusiastic and happy to help Alan with this quest to try to find more affordable ways to detect microplastics, and in my case, in food and water. And we're hoping that at some point we could use some of the methodologies and the techniques that we identified in this effort in our own work at Consumer Reports. So thank you, Alan, and thank you to the crowd. And I'd be willing to answer any questions about CR's microplastic interests.
Yeah, and I'm also going to bring in Scott Coffin here, who is a toxologist and thinker around public health. Hey, Scott, anything you want to add in your own work to that rundown about kind of what microplastics are, where they represent in the health world, what you think about them?
Sure. I mean, Dr. Rogers did a fantastic job, but I'll just add that this is a global priority. The World Health Organization has released two major reports on microplastics in the last 7 years, and Europe, as well as California, New Jersey, and a couple other states in the US, are gearing up to have comprehensive microplastics testing programs in drinking water. And critical to the implementation of these plans is having a method that can quickly and cheaply identify microplastics. So this is a very high priority for scientists, regulators, and the general public. So I'm really pleased to see this challenge that Consumer Reports put together.
I'm also just flagging that I do see questions coming into the Q&A and I appreciate them. And I'm gonna, you know, put all three of these current questions and some of the ones I'm seeing in chat under the same, general category, which is what can I do about this? We're going to do some of that today on the call, and we are going to drop in some links and things about Consumer Reports reporting on the issues of water purification systems, how you can eat less plastic, what you can do in your life. But the real goal today is where Jim and Scott are talking about here, right? We're talking about like trying to understand much more holistically about the scale of the problem and the ways that these microplastics are getting into our water sources and how we test for them writ large. So just to flag, like we will have a little bit of time for those kind of individual questions, but we're really going to be focusing mostly today on systemic testing and systemic fixes. So, to that end, how did we get to a place where we get to have winners to talk about? I'm going to bring in Samantha, my colleague from Lifeguard. Come in, Samantha, say hi, where you calling in from, and tell us a little bit about Lifeguard and your work and what you do.
Hi, everyone. Thanks, Alan. I'm Samantha. I'm calling in from Vancouver, Canada today. And I'd love to share a little bit about Lifeguard, how we got here. So Lifeguard, we're an early stage nonprofit. We're on a mission to bring the power of crowdsourcing and other open source research methods to underserved human health and environmental issues. So first question you might have, what is crowdsourcing? This is one definition. It's an open call to an indeterminate group of people, bringing together those best suited to develop the tasks, respond to complex problems, and contribute the freshest and most relevant ideas. So that's exactly what we've tried to do with this challenge, and seem to have generated a really interesting solutions for this particular challenge. We sent the call. What we do for every challenge is we send the call out to anyone and everyone in the world, around the world, who comes across this, who we reach out to participate in this challenge, whether they're professionals, scientists, hobbyists, innovators from all different backgrounds. We invite anyone to join. We do have a dedicated community of innovators, scientists, and people of all different backgrounds as part of the Lifeguard community itself. But the important thing to recognize about crowdsourcing is this open call to anyone to join. So this particular challenge, we had participants from 37 countries from every corner of the world, which is really incredible to have these truly global approaches to solving a problem that affects all of us, as Jim already mentioned, the highest mountaintops, the bottom of the ocean, and so forth. So we believe this approach really has promise to solve these, some of these biggest problems we're facing as a society. So the premise of Lifeguard, why we started in the first place, was really simple. We saw that Fortune 500, some of the biggest companies in the world, were using this crowdsourcing approach all the way back since the early 2000s, even in the 90s, to solve their R&D problems. Let's say they needed to substitute an ingredient in a detergent. What they did, instead of hiring someone or consulting with a particular firm, they would send out these open calls to action. And they actually found it to be very effective, more cost effective, to get solutions in faster timescales, and to really bring fresh ideas to their problems. So that's effectively what we're doing with Lifeguard. We're calling in different organizations that are concerned about these issues that affect all of us, helping them curate challenges and sending them out to innovators, scientists, experts all over the world. So if you'd like to learn more about what we're doing at Lifeguard, you can go ahead and scan this QR code and learn more about us on our website. We'd love to have you part of this community going forward, whether you are technically interested in participating in challenges or just learning more. We also would love to hear from you and what issues you're concerned about. We're going to be continuing to put these efforts towards different issues. So we'd love to hear what sorts of challenges you'd like us to run, and really kind of serve all of our best interests. So that's a little bit about Lifeguard.
Thank you so much, Samantha, and thank you for your partnership on this work so far. Two quick things to flag. One, if you are watching this video on your phone already or you're on a laptop and can't get to that QR code, don't worry. Again, this will go around in the email after the fact as well, in addition. And then the second thing I'll flag is to say some of you, some of the names that I'm seeing on this call that I've seen before, and some of the people who are kind of participants in the community reports project, which is the work that I am fortunate enough to lead and work on here at CR, is really a lot about crowdsourcing. It's a lot about how we as a collective can learn more from from our collective knowledge, how you are all out in the world participating as individuals in different marketplaces and feeding some of that information back to CR. So, two things about that. One, shout out to the community reporters who are here. Y'all are awesome. Thank you for being here. And two, the opportunity to partner with Lifeguard was a really great chance for us to explore a slightly different definition of crowdsourcing from ours, which is to say their community is people who are already experts in a lot of cases in a lot of ways, and to being able to tap that expertise was really exciting for us, and gets us in a seamless transition to some of the people who we met over the course of this process. So I am going now to invite Team 1 all to come back on camera and off mute. I will, I think, toss it to you, Nur, to start out, but say hi and tell us a little bit about it's y'all's show. How do you want to take us through your awesome idea?
All right, awesome. Sounds good. Thank you, Alan. So I'm Nur Ali Faturrahman. I'm on air from the Kingdom of Saudi Arabia because I still research here, do my PhD in chemistry. So actually, as a PhD student and also as a parent, the microplastic are not just a scientific issue for us, and they are like a personal issue. So because if something is entering our homes and our bodies, we deserve right to detect it. So here with my incredible team and the right timing of the challenge from Lifeguard, Consumer Report, and Hero X, we finally find the opportunity to introduce our kids as a small contribution to the community to help people detect the microplastic at home in just a few minutes. And let's listen the explanation from my colleague, Esra Kotob Abbas will explain it to you in detail. So go on, Esra.
Hi, everyone. Thank you, Noor. And thank you for Lifeguard for this amazing opportunity to participate in this. I say that it was amazing journey for us because it started in special time for me and Noor and Listia. We were in another competition in Norway for carbon dioxide sensor with Climate Summit. And that time we started to participate in microplastic challenge, and all the way when we were just going back from the competition, we were thinking like how we can find the solutions that convert every one of us to the scientist of environment. Like if you have a sample of, you can detect the microplastic and know that your sample has microplastic or not. How we can do this in simple way and very cheap, because we believe that if everyone can see the problem and know about it, we can find a solution easily, because every problem started with how you can define this problem and how you can think about it and know how it's dangerous for your life, for your children's life, for another generation, and you can solve it easy after this. So from this point, we get an inspiration from Corona test. All of us see what happened in Corona. All of us in the home, and we have to find a solution and find the test to see if you have Corona or not. So we get inspiration from this idea to make a special kit, very easy and user-friendly, how you can detect in any sample of your sample, like food, juice, or water, how you can find if your sample has microplastic or not, by very simple way. We started to think about a kit. It's consisted of the spray and UV lamp. We just depend on this in something friendly and every one of us using in home, which is spicy, called curcum. This curcuma is using every home, especially in Arabic region, every home of us is using as a spice. So, but it also has a nature of chemistry like high fluorescence, which can interact with UV. From this point, we started to think how we can use this friendly material with UV to detect microplastic. And then we synthesized the spray. This spray is curcum, based on curcum in just diluted solution with some nanoparticles material, and also combined with some polymer, but all of them in small portion to make this kit. And then you can spray it, grind with your material, and then spot it by the UV lamp for only 2 or 3 minutes. And then you can get detection like your sample has a fluorescence for microplastic or not. By this way, as you can see in the second picture, you can see that the color of the fluorescence, if it's a very high color, green color, you can see that your sample has microplastic or not. By this way, we convert everyone to the microplastic in scientists like can detect and can analyze any sample. And from this point, we started to think big. This was the first step for us, like, oh, now we make everyone know that the sample has microplastic or not. But we want something to be global, because this is not issue for just temporary. It's an issue that we have to find a solution for it. So we think about what we called it platform. This platform would be like a Google Map. It's map for microplastic pollution. Everyone use our kit will just register in this platform and say, send the picture for his sample or her sample, and then this will be our data to train a model for artificial intelligence, so can analyze the data in the future, and then can help the people like consumer report, or help the industrial people how to solve the problem in different regions of the world. Like this place has so much microplastic for different product. We can just make a navigation for the consumer, like don't use this brand because it has a lot of microplastic, so you have to be aware before you use it. So we can also help the industrial to take care about the consumer, like they now know, and they started to become a scientist of microplastic. So we teach them how to analyze the data, and then how to be the part of the global platform for microplastics. So this is our inspiration from Microplastic Kit, and we hopefully to go to the step now for quality control, and started to the first step of the pilot test, and started to see our consumer what we say about our kit. So thank you.
Thank you. I want to just flag a few things that are popping up in chat as you were speaking. Claudia, you're in the right place. This is a safe space for nerds. Welcome. Two, I want to flag sort of 2 questions that I'm going to toss to you all now as a team for you to figure out how you want to answer. But Douglas asks, how do you measure number of particles and different sizes? Says laser light scattering will do, but one needs standards and controls, which may vary for different plastic types. Interesting question. And Ale asks, how do you prepare the sample for food as opposed to water? And Jess, yes, we will have a link to rewatch this. So if you have to duck out, we will miss you, but you will have another bite at the apple.
For the first question? Yeah, for the first question, it's amazing because it will be our next step now, because we want to go to the control experiment, which we need more work about the particles of the microplastics that we are going to detect, the size of this particle, and also the time or the consumer for this spray, how long it will survive with the consumer. This is all of them is we called it control experiment. This question is one of our control experiment, which we are going to do in next step, which is amazing because we want to be more precise, because you're talking now about just a spray to mix it with your material and get the indication that you have microplastic or not. But microplastic is different type and different size and different technique. That's why this is a control experiment will give us the opportunity to see which size we are dealing with, what is our limitation, because for sure any technology has a limitation and some obstacles, so we will face some challenge, so to know how to solve it. So this question, the answer is that it will be in our control experiment step. And for the second one, it's about already, if Noor can share the barcode, we provide a video for how the consumer can deal by this kit, like how you can grinding with any different sample. You can grind a different sample with a spray and wait after you spray on the sample 3 or 4 minutes until it will dry. Then you can spot by UV. So if Noor can share I don't know if barcode is not here for our video. When we share this video, we make a video how you can use the sample, how you can prepare your sample, and how you can spot the UV so you can get the data, right data for your sample.
Amazing. Thank you so much. I want to bring in the other idea that we're going to be featuring today, but I also realized that I didn't put this slide up for a second. So is there anything you all want to double back to? I'm seeing suddenly that one of the Listra's connection was going in and out. So if she wants to come in, you are welcome, if you can hear me, to come in and inject in the conversation as well. But I want to throw back to you, Noor. Anything you want to highlight from this slide, or from that you would like to put a finer point on anything Esra just said?
Yes, of course. So sounds good, Esra. Thank you, Ellen. And this slide is like the detection workflow that we develop. So for food, of course, we first break down the food matrix into the liquid using our organic solvent like ethanol. It's safe solvent. And then we do the jettison step, and then we filter and analyze the microplastic itself, just like the water sample. And then for our experimental, also not only the water, we also do for the snacks, for the carrot, for the fruit, and for any kind of juice. And this is the scoring guide in the right of the slide that will be guiding us as the consumer to use our kits, and then will report in our current development platform. So it's like the reason we develop this is our principle is to develop a non-toxic bio-based detection kit for, of course, the rapid and user-friendly testing. And then now we work on to patent the process. And of course, in the future, we will eager to help and engage for all stakeholders in microplastic education and awareness globally. Thank you, Ellen.
Yeah, and I think there's a question in the chat that I think I can answer, but I want to give you a chance to answer as well. What's the smallest particle that we are hypothesizing that this can detect? Is it have to be by the naked eye, or how small are we imagining this gets?
In this step, in this stage, we can just by naked eye, we can see it like. But maybe in the future, if we can develop our kit more, we can go to less smaller size, which is our target, because we want to get viral. But it will be different kit for each one. Like if the smaller size, it will go to another concentration for the spray and for the kit preparation to get a detection very well. So until now, we are not into the very going depths, like very small size, we can see it, but now we can deal with the particles we can see.
All right. I see a bunch of questions flipping by in chat, and I would love to invite all three folks from this team. Listy, I see you are back with us. So if you want to jump in and say anything, I will give you that moment. But also, I would love for you, if you guys want to jump into chat and see if you can start answering some of those questions there. That would be awesome.
Sorry, I have
Yeah.
connection issue
No.
previously. I just want to add what Esra said before about our data and results. For our kit currently, we can detect microplastic maybe in size around 20 until 30 micrometer. It's depend on the camera. And of course, for our kit, it will works on like the common plastic like PET, PP, PS, HDPE. And yeah, again, it will works in water and many food liquids and designed to be simple, cheap, and accessible. Yes.
Amazing. Yes. So to return for a second to the scope of the challenge that we put forward to everyone, we wanted folks to address speed, cost, and also size of microplastics, right? We knew from a jump that it was very unlikely that any one solution would be able to nail all of those things easily across the board. And one of the ways that we were sort of ranking and reviewing these amazing entries from around the world that Samantha was referencing is through how each one did in, how many of those different areas they hit, and also how innovative or how new or unusual we thought the idea was. So, Syed, welcome into the conversation. We gave your idea the most innovative, most interesting, most kind of outside the boxy winner. So come on and tell us a little bit about your theory, and then I'm going to put Jim and Scott on stack for any kind of questions or clarifications that you want to get out after Syed has a chance to share.
Hello, everyone. Thank you for joining. My name is Syed Ahmed, and I'm one half of the plastic cell detection team who have won the runner-up in the microplastic detection challenge. My teammate is my brother, Syed Ahmed, who is a biotechnology graduate. So we developed a cheap electroimpedance spectroscopy biosensor, which uses plastic degrading bacteria which is encapsulated on a graphene oxide mesh probe, which can be connected to this circuit. And the resultant impedance time series graph is generated at the end, which is fed into a machine learning model, which predicts if the microplastic is present in it or the type of microplastic present in that food sample. Next slide, please, Alan. So what is a biosensor? A biosensor is anything biological or chemical which attracts or attaches itself to a chemical or biological specimen, causes changes in it, and these changes are recorded and captured by the transducer, which converts it into actionable or understandable data. EIS, the system I've used in my idea, works similar to Raman spectroscopy, which is generally, as James has told in this slide earlier, that this is used as part of microplastic detection because it can detect Raman scattering and filter out the Rayleigh scattering, and it can be able to determine the presence of nano and microplastic present in a food sample or anything. So my idea leans on measurement of impedance in a food sample. So we have bacteria which degrades plastics. We have different type of bacteria for each plastic, and they are able to degrade most of these plastics used in the food specimens. Like we have polypropylene, we have polystyrene, we have polyethylene, and we have polyethylene terephthalate. And so what these bacteria do is they degrade these plastics, they release ions and cause the change in this impedance, which is noted down and fed into a machine learning model, which predicts if the microplastic is present in it or not. Can I have the next slide, Alan? So this is the representation of what it looks like. We have a probe, mesh probe, which has the perforations in it, and each perforation has encapsulated bacteria which is stuck on this mesh. So when it comes to what comes in contact with a microplastic or even a nanoplastic, it depends on if the bacteria is able to degrade this nanoplastic. And once it comes into contact with the microplastic, it is able to degrade it, ions are released, and the impedance changes. So the circuit consists of AD5933 and ESP32 controller, which are cheap and is connected to the user's device. So what it does is notes down, creates a time series graph, which has the impedance data for about 45 minutes per probe. So the glass dish you can see in the image has the food sample, and once the bacteria comes in contact with the microplastic, it starts degrading and the impedance graph is created. Can I have the next slide, please? This is the procedure that this idea uses. So we take a glass dish, we take a semi-solid, solid, or liquid food sample, we put it on the glass glass dish, and we add a buffer which consists of chitosan and sterile water. What chitosan does is it coalesces the oils, excess oils that could interfere with bacterial degradation. We remove most of these, and the probe is inserted into this food sample. The mesh probe has these encapsulated bacteria which break down the microplastic, and you can see in the last one that the impedance changes. Can I have the next slide on? Once we get this impedance graph, it is fed into a deep learning model, which which finds any discrepancies, flags any anomalies, and makes predictions on the basis of what it was trained on. If you have a big enough data, it is able to predict the presence of microplastics, what it usually does, gives us the type of microplastic present in it. It also could predict the cause of how it got in there and the shape of the microplastic because if we know about it, we can flag and crack down entities that have been creating poor packaging, because of which microplastics and nanoplastics are getting into our food. So this idea could be useful in to control and to have a targeted control of microplastics in an age where microplastics, and nanoplastics are ubiquitous. So this plethora of data is essential to help in a control of microplastics and nanoplastics. Thank you.
Thank you so much, Syed. Lots of good questions and discussion happening in the chat right now about all things. Why is this important? What we need from all of this? Why we're doing it? I'm actually gonna stop sharing on my screen now because I think that's mostly all the slides that we have to get through today, and I'm going to, like I promised I was going to, I'm going to serve you, Jim, Scott. We're going to clear out for a second and let you guys come on and ask any questions, or also you guys have seen these questions rolling by. Is there anything that has jumped out at you as interesting that you want to unpack? Yeah, Jim, you go first.
Yeah, I think that one of the statements was that we kind of know that microplastics are in all water and food. Yes, but. And I think that for me and my team, we're worried about the amounts, but we're also worried about the type of plastics, because if we consistently see a certain type of plastic, that maybe we can start regulating or reducing the amount of use of that plastic, especially if it's associated with particular chemicals that are used to make the plastic. And I think especially like for baby food, baby formula, we want to reduce the exposure of these babies to these chemicals. And if, at least from the microplastics area, if we could start telling the type of plastics, etc., maybe we can target our efforts to get microplastics reduced. So that's why I think it's important to test and hopefully identify the type of plastic being used. I accept they're ubiquitous, but I still want to know what is there, because then we can advocate for some type of control or reduction. So I guess the question would be, when will we get to a test like these two researchers have presented to us that could possibly identify the type of plastic that's in there, if possible?
Scott, which thread do you want to pull on?
Oh boy, there's so many different angles. Well, I'm really curious about the biosensor technology, where the idea for that came, Saeed. if you could provide a little bit more information about other uses for this type of technology that you've worked with or you're familiar with. I just think it's a very I don't want to say like left field in like a negative way, but it's refreshing to see something new in this space that has been very well explored. So I'm really grateful for your contribution.
The biosensor bit, I actually saw it on a research paper, but they haven't used bacteria to break down the microplastic. They have just used this impedance biosensor to detect any heavy metals present in the water. I think it was in one of the research papers I recently saw, and there has been quite a lot of study on the impedance used to determine what kind of material is present in a particular water or other substances. So I think this could be influential in finding microplastics if it is paired with machine learning models. And if these machine learning models are trained on a plethora of data where control systems and control data and different kinds of plastic data is used to train these machine learning models, we would be able to find not only the presence of microplastic, but also the shape and maybe how it got there in the first place.
I'm going to, offer the same opportunity to you, Samantha. Anything you want to pull on, but then I'm also going to flag there's a bunch of questions. Again, not all that we're going to have time for, asking, everything from microwavable bags to PVC pipes to I saw a question about fleece clothing. Should we burn it instead of disposing of it any other way? So, if anyone wants to speak a little bit more about different sort of known contaminants and things that, we dropped an article in there and we'll drop it again to say like, hey, here's how Consumer Reports thinks you should eat less plastic. But like, where is this stuff coming from? What's the number one thing that you avoid, Jim? What's the number one thing, Scott, that you're like, not in my house? Anything like that? Jim, you're talking on mute.
I think we've talked about at CR again, reducing the amount of plastic use in the kitchen. And I've been interviewed a number of times where I said we've eliminated as much plastic as possible for reheating our food or storing our food. The one caveat I would say is using freezer bags in the freezer, because there's really not an alternative unless you use disposable plastic, which is plastic or foil. And so what we try to do in the Rogers household is not use as much plastic, not purchase as much plastic, not reheat in plastic at all, just to try to reduce our plastic footprint. So that's one thing I can throw in there.
Those are great recommendations. Yeah, really avoiding the heating, I think, is the major one that you can implement, and it's quite easy. The other main source of microplastics exposure in the home is from our textiles. So the clothing we wear, the upholsteries, carpets, and rugs that we can put in our homes is something that we can be more conscious about. The synthetic fibers are constantly shedding, going up into the air. We're breathing them. They're also falling into our plates that when we eat food, cups when we drink water. So you can install an air filter if you can't change the carpet or rug in your house that's synthetic, and choose more natural fibers in our lives.
I'm gonna open it up to any of the panelists who want to get in on this as well. Sort of like Nura, you spoke about your dual lives as a chemistry PhD and as a parent. How is this ookieing back into your life? How has this knowledge changed how you live?
Yes, so I think this issue and the solution of idea matters because it gives power back to the people, right? So now during this challenge, microplastic should not be a mystery again. Parents should know what is their children food, and students should know tools to learn about the environmental health, and the communities should be able to report, to track, to talk about the contamination of this microplastic. And this, we hope that families can not only detect the microplastic, but also like upload the result of their detection. So this can build the first global map of the microplastic exposure from the kitchen to the communities, and finally it will turn the detection into the collective awareness. So again, by making the detection simple and low cost, we hope we can, as the student, as a researcher, we can inspire the worldwide to shift toward a safer food and healthier living.
I'm going to take moderator privilege here and throw a question to you, Scott. I saw a couple questions zip by about what testing is happening in California and whether or not that is something that, we can learn from here. What's the bleeding edge out where you are?
Thanks, Alan. So we currently have two standardized analytical methods in California that use Raman and FTIR spectroscopy. We provide accreditation for qualified laboratories for these methods, and we currently have 3 accredited labs, 2 commercial and 1 nonprofit. And these labs will be processing drinking water samples from approximately 30 of the largest water systems in the state of California over the next 4 years. And so if you live in a large metropolitan area in California, expect to see some information about how much microplastics are in your drinking water supplies.
That is, yeah, thank you. Let me see. I'm having trouble figuring out which threads I want to pull on. There are too many good threads. Samantha, do you have anything that you want to flag here as we come down to the end?
I'd love just to send out to or ask the both teams what they see as their next step in terms of. I know we heard a little bit from the Spot MP team, but concrete next steps and kind of working with these solutions and getting them out there.
I would like to answer that question. I hope some researchers or scientists take over the EIS research more often and create the machine learning model more strongly so that we can predict the presence of microplastic easily. So it's necessary that the researchers around the world take more interest in the impedance spectroscopy because we know Raman spectroscopy is quite costly. So I think impedance spectroscopy should be the future ahead, and it should be more strongly used alongside biosensors in order to find these microplastics because we have a plethora of bacteria out there that may degrade plastics. And quite recently, AlphaFold 2 is making progress with their AI models, and they're trying to create an enzyme that breaks down all kinds of plastic. So if that happens, maybe we would be able to detect microplastics more easily going forward.
I would like to answer from my Spot MPAI point of view. So for our kit, we definitely will improve our kits to be better sensitivity, and also we need to reduce the food interference noise, and also of course for the accuracy for the AI itself, we have to enhance the sensitivity also for the accuracy in AI. And also we plan to make like the educational kits so everyone can understand more about how our kits works.
Amazing. All right, we have 3 minutes left at the top of the hour. So I'm going to rapid fire say thank you, John. I'm glad we exceeded expectations. Thank you, Greg, for your inputs here, and a couple of people who have been sharing, what you all know about water filtration systems and how people can do things to keep themselves safe. I think that the set of links that we will be sending around after the fact will help with some of those things, but I also think that there's a lot about over-the-counter available water filtration systems that we're pretty sure don't quite get down to the level of the nanoplastics that we're talking about today. So they should not be viewed as a solution along those lines. We have to work together to get things out from further upstream than that. And then finally, a couple great questions. Thank you for all these amazing questions, and there are too many for us to answer, but a couple great questions from Stephen and Vanessa. Stephen asks, has the team looked at models for implementing citizen science programs, a la adopt a stream, air quality monitor, weather station, storm spotting, etc.? And Vanessa asks, what about getting more young people involved with this? First of all, you just got to meet some amazing people who I think you guys would classify yourselves as young. I don't know. You seem young to me. I think you count. You're in. Thank you all so much for being here and for doing this. But I think the larger citizen science program point is that we need the ability for everyone to be able to go out and test for this stuff. And I think that that's the missing piece to get us to an air quality monitor program, a weather stations program, an adopt a stream kind of a program, which is where these two amazing teams have, I think, helped us advance the ball a little bit. Everything that came from the 72 submissions from across the challenge is open source. It is available for anyone to come look at. These awesome teams, hopefully we will get to continue to work with to move on to the next step. But our holy grail is still to get there, Stephen. It's still to be able to have something that we can offer you all as our community of citizen scientists to go out and to look around and to help us build a larger collection of information about the world. With that, we are exactly at 1 p.m. Eastern Standard. I think some of these folks have been staying up way past my bedtime to talk with us tonight. Thank you all so much. Kathleen, you're right. There's no option at the top of the chat. I will be taking the chat, grabbing it all, putting it in the email with the video. I'll put it in there with all the links. So all of that stuff will be coming to you tomorrow. And one last thank you all for being here, for your time, for your investment, for your great questions. And to the two winning teams, congratulations and thank you. Y'all rock.